You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that had, has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and share it with friends. Thank you. Hello, this is Richard Jacobs with the Future Tech and Future Tech Health Podcast. I have Dr. Moshe Szyf. He received his PhD from Hebrew University, did a postdoc fellowship in genetics at Harvard Medical School. I currently hold a James McGill professorship at GlaxoSmithKline, chair in pharmacology. Many accolades here, and we're going to be talking about his work on social epigenetics. I'm not sure what that means, but Moshe, welcome. Thank you for coming.
Thank you for inviting me.
Yeah, what is social epigenetics, or I guess more simply, what is your current work about? What's it entail?
I have been working on epigenetics for the last 40 years, trying to understand essentially how genes are programmed and how different experiences in life change the way genes are programmed. And that leads us to social epigenetics, realizing that not only chemicals and hard stuff can change the way genes work, but also social experiences can change the way genes work. And that created, for the first time, a link between social sciences and hardcore DNA.
So, okay, I guess, if I smoke cigarettes or if I work out a lot at the gym, I'm turning on and off genes, or, I'm affecting my epigenetics, and it doesn't seem too far-fetched. I've wondered, what if I sat there and meditated, and did this for a period of weeks or months or years, if that would affect my epigenetics. But, when you talk about the social side of it, what have you seen that maybe is surprising? How can people affect their gene expression in ways just simple ways?
Yeah, we need to differentiate between two ways by which genes can be affected. One is, of course, if you're exposed to something, you turn on and turn off genes. That's what genes are supposed to do. But that's not what we're talking about. We're talking about changing how the genes are programmed forever or for a long time. So you're exposed to a cigarette now, and then 20 years down the line, the effects of that cigarette will be seen on your gene. So that's epigenetic programming, in difference from just programming gene expression, which is the immediate response to an exposure to a cigarette. And so in a certain way, we're changing the way our genes are by experiences that extend well beyond the time that the experience had appeared, which means that everything has a consequence. And the consequence is not just the immediate consequence, but long term. For the first time, we noticed that it's not just chemicals that can do that, although even that took a long time to understand that, exposures don't only change things immediately, but actually change the way genes are programmed for a long time, and perhaps even for many generations. Was an experiment that we did here at McGill with Michael Meany, where we looked at maternal care in rats and how differences in maternal care, which is a very classical, social behavior, affect the way the animals will develop. So when the animals are adults, they'll have completely different characteristics based on the way their mother treated them years before. And we asked the question, how is this possible?
Yeah, I think I heard about this. There were rat mothers that licked their pups
a
Right.
lot and some didn't. And okay, yeah, can you go over what happened in the experiment again?
So, in this study, it was first an observational study that rats that lick their pups more frequently, their pups, when they grow to become adults, they will have different stress responsivity, different what we call phenotypes, different characteristics than rats that were not treated as frequently. So high maternal care shapes the lifelong behavior and physical characteristics of their offspring. And how is that possible, right? So we try to understand how is it possible that this works. We still believe that everything is somehow connected to the way genes work. So we reason that what is happening is that the maternal behavior is changing the way genes are programmed in the pups. And that really launched this field of social epigenetics when we discovered the epigenetic changes that are initiated by maternal behavior, but then remain well after the mother is dead.
Well, I mean, in humans, if you beat your children or you abuse them, they tend not to grow up and to be too well adjusted. So similar phenomena, I guess, different creature. But some, I guess, would try to say, oh, that's just, their mental responses and not physiological changes. So you've observed literally different physiology from rats.
No, not just physiology. We observe differences in the chemistry of DNA. And so these are not just hand waving, kinds of, you
right.
and things happen. The question is, how do they happen? Why do they happen?
When you say changes in the DNA, does that mean like different methylation patterns, different histone deacetylation patterns,
right.
that kind of stuff?
Exactly.
Wow. Okay. What about, do you see different changes in the underlying DNA itself, or just at the epigenetic level?
The sequences do not change. And here is the thing. We inherit. Their sequence lasts for life, and it stays the same in every tissue in our body. That cannot change. But the way they work can change. And, before that, the main emphasis was on genetics, on, genetic differences that can explain psychological, behavioral, social difference. But what we discovered is that the overwhelming force is not really the genetic differences, but how your genes are put to work by experience.
Okay. Well, how do you profile someone epigenetically? I would think every different cell type reacts differently, or do a lot of them act in concert under a stress response?
So, there are things that are different and things that are the same. It has to do with the job of the gene. Certain genes need to work in the same way in across tissues, and others are highly specialized. Stress is something that covers the whole body, although it will have different effects in different tissues. Stress affects the immune system, it affects the brain, it affects fat, it affects metabolism. So it's integrated across the body, and therefore it's not surprising that you'll find some changes in DNA methylation that will be common to a lot of tissues and others that will be different.
Okay, so how many, in determining this, how many different cell types did you look at? And, I don't think you looked at all of them, so maybe you did a subset and you said, all right, well, it's probably likely that this applies to all of them.
Of course, not all of them. Although we would love to do it. It's just a financial issue.
Right.
That's a project that will cost in the billions. But what one can do and what we did, we first looked only in the brain. And we only looked in very specialized areas of the brain that are highly responsive and controlling stress. But then we found that it's not just the brain. To our surprise, the immune system was also affected. And so we looked at the immune system and the brain. Other people look at fat tissue and muscle tissue. You're quite limited with what's accessible. Of course, it will be extremely interesting to look at the thousands of cell types, how they respond to this kinds of social signals early in life, and how these signals evolve during life.
So what have you figured out? What's the mechanism of epigenetic change? Have you figured out any of the mechanisms and what the pathway would be?
So, this is an area that is investigated quite aggressively by a lot of people. In our original study, we kind of deciphered that there is some sort of a pathway leading between, maternal behavior, releases. This is an area of active research by many groups, trying to figure out how experience leads to very particular changes in the way genes are marked. In our initial study and follow-up studies, we focused on, the stress response pathway and how maternal behavior elicits certain hormones, certain neurotransmitters in the brain, like, for example, serotonin, which is released when you feel good. That neurotransmitter acts on what we call receptors, proteins that can receive the signal, and then a series of proteins that are connected to each other, leading to what we call transcription factors, which are proteins that can find addresses on DNA the same way a postman can deliver a mail to a specific address. They can read the zip codes on the DNA and target DNA grooming enzymes to particular sites. So this way, the maternal behavior ends up in particular addresses in the genome.
How would it know where to go in the genome, and how to, let's say it's going to methylate this one part of the genome. How does it know that part is the right part to methylate, for instance, and how does it know that part may not be used for other types of genes in gene expression to make, hurt the expression of other ancillary genes, because it uses a common area that other genes use?
Of course, there will be using, none of these systems is perfect, but it's the combination that creates the perfection, and that evolution has probably generated transcription factors that on one hand can recognize specific, DNA addresses. On the other hand, they can be kicked in the head by signals coming from the outside world. And not all cells are going to change. So there's speciation in which cell types are responsive to that signal. So in the hippocampus, there are millions of neurons. Only some of them will change. And why these neurons and not others? This is why we have evolution, is to figure out these things by trial and error, which are the things that increase fitness and others that don't. Transcription factors can read very specific addresses in the genome. They can also talk to signaling that comes from the surface of the cell. So they can connect the surface of the cell with the addresses in the genome. Do we understand everything? No. The complexities? Of course not. But we have some hint how these things work.
What are some elements of this whole system that you'd love to understand? For instance, what is the DNA indexing system? What about that? Let's say, as an example, one of the elements of this whole, epigenetic change, you said there seems to be the ability for compounds to index the DNA and to go to a very specific location and know that that's the right location to do their work.
They don't know.
Mechanism alone. How does that happen?
This mechanism is very, very well known. So transcription factors, the way their protein is structured, they can see certain sequences. So we have evolved a whole battery of transcription factors that can go to different parts of the DNA, and they know how to get there. This is actually quite known. How all of this makes sense within a context of an environment, it's very complicated, and it's beyond my understanding even how to approach it, because we have a combination of things that happen. How things can see specific addresses in the DNA, that's simple. How is this good for us, and how an early experience knows that sending the transcription factors to these places in these cells is what will increase their fitness or their survival or the long-term well-being. We don't understand that. And that probably required trials and errors of evolution to figure this out.
So what in particular are you focused in on? What do you want to elucidate? Is it the overall ability of this to happen at all? Is it to predict?
No, I think that's
happen?
That's known. We're interested in different questions. One question is how to take advantage of this to predict disease early. This is one area that I'm very interested in. The second area is how to take this to therapy, how to apply epigenetic principles and intervention. And the third area, of course, is still there are many open questions about how methylation affects gene expression and how other forms of modification like hydroxylation, formylation affect gene expression. So there are a lot of mechanical questions that are still open that need to be understood. But I would like to jump and move forward without understanding everything and seeing how we can use it to predict disease early, problems early, and to prevent them.
Well, for instance, how would you envision using it to predict disease?
And for example, can we predict Alzheimer's early? Are there methylation signals in blood that tell us that that person is developing Alzheimer's? And if we can do that, there are many probably already available therapies that might work. And the failure of Alzheimer's treatment is not that the drugs were not good, is that when a person knows they have Alzheimer's, already the brain is dead. And so it's very hard to treat a dead brain. But if you can capture it before the brain has died, or before the parts of the brain that are important have died, then some treatment might work. If you look at cancer, cancer is a disease that could be cured if detected early. But in most cases of death, the causes of cancer are late detection. Can we detect it early? If you look at aging, which is another aspect that, where epigenetics is actually driving the process, if we can detect acceleration of aging early, perhaps certain interventions could prevent that from happening. So there's so much to do and so many opportunities in using those programs to detect disease early and to intervene and prevent deterioration.
Well, what appears to be the most direct link to epigenetic change? Is there a particular condition that's been identified as, having a radical effect on epigenetics, or are you looking for ones that have a very specific effect on epigenetics and only affect a few discrete areas? Because I would guess if you can elucidate the mechanism by which some kind of disease causes a change or is correlated with a change in the epigenetics, then that might be a good way to attack it.
Of course. So in cancer, this is quite developed. We know a lot of epigenetic changes that are involved in basic processes that are driving cancer. And of course, there's already attempts to, try different therapeutic approaches. But I'm talking about two different, you're mixing two different things. One is early detection, which really doesn't care if it's connected to the mechanism as long as it works. And the second one is treatment, which tries to reverse changes that are important for the disease. And in both areas, progress is made. We're not looking for specific things. We're looking for treatments that can essentially shake the epigenetic system and kind of reverse it to a more tolerable state. The epigenetic system is affected by everything in our life, so there's no particular thing that affects it. At some point, it changes in a way that is not good for us, and the question is, how do we bring it back? There are also many different things that can bring back the epigenetic system, from nutritional supplements to exercise to lifestyle changes and other things. And these are things that need to be worked out.
Well, if you understand how, for instance, epigenetic change can happen, you need to understand that to undo it, I would think. And then you look for specific changes and try to watch and figure out all the steps in which they happen, and then try to undo them or prevent them from happening, for instance.
Right. But yes, of course we want to understand this, but I'm not sure that will help us undo them. I think the way the system works is as a system. So it's not like there's one change happening. There's multiple changes happening. And it's not the specificity of the change, but it's the specificity of the combination. It's the setting of the network. And so you want to reset the network. It's very different than, fixing one or two changes. And the way to reset the network is probably by shocking the network. And this is what we're trying to figure out, what are the shockers that we can shock the network. Exercise is resetting a whole network. Differences in diets are resetting networks. Going to a vacation is probably resetting networks. And to figure out the combination of resets that we need to achieve a better, state of the network is the challenge. So we have to move from the classic way of thinking about a specific change and a specific outcome to systems, resetting to different states. This is the main challenge in this field.
What about in cancer? I mean, I would think that cancer cells change their expression, but that's happening within a given population of cells. So I'm sure they're interacting with the network around them, but it seems like the cells are the ones that are doing the measuring and the adaptation at that individual cellular level in cancer. So perhaps that's an easier way to figure out how this could happen or be undone is by looking at cancer, because again, it seems to be less of a systemic response or a very, very small system, the tumor itself, for instance.
I'm not sure about that. And so I think that's the classic way of looking at it. But even in cancer, when you look at the methylation system, the change is thousands. We're not talking one. And so we can reset the system by sometimes simple manipulations. And so the idea that, yes, there are certain cancers that develop certain, surface molecules that could be targeted by drugs, and that is really working well. But overall, cancer is a systemic change in the way thousands of genes are working. And so a more basic approach to treat it is to figure out a way how to reset that system. And also, cancer is not just a disease of cancer cells. It's becoming very clear that the immune system is highly involved in cancer. And some of the new therapies actually target the immune system. The immune system is the host. The immune system is all over the body. And the immune system is also regulated by the brain and by other experiences. So at the end of the day, I think we're moving from, the reductionist approach to a more holistic understanding of how the system works and trying to figure out how to alter the system. I believe that even in cancer, overall, holistic solutions will be probably much more powerful than what we have now.
Well, it just seems to fly in the face of, neo-Darwinist dogma. And for instance, with cancer, it's a random mutation that happens in a single cell. Well, that's not a system. That's a single cell. That's not a system. So it doesn't seem, the two seem to be at odds. This is an adaptive response, a purely adaptive response. It's not a random thing. So this seems to be at odds with, again, the common perception of the neo-Darwinism.
It's not clear that cancer is actually triggered by mutation. And some cancers are, but others probably not. And again, it's not clear that one mutation can drive cancer. And probably that's not true. And is cancer really a selection, or is it a defect in the immune system? Are cancer cells unnatural, or they're part of the natural system that goes out of balance? And within the genome, again, we're talking about thousands and thousands of genes that are changing. And the problems with curing cancer is the redundancy of the system, is that we are trying to target molecules rather than targeting systems. And so, one of the things that works the best is chemotherapy, because it really targets the whole cell. It kills the cell. And so specialized targets work in very, very few cases. But overall, every cancer cell is a systemic change. When you look at a methylation profile of a cancer cell, you can see an enormous change in many, many genes, all of which are important for, cancer survival. A cell is a corporation. And to change the strategy of a corporation, you can't change just one guy. You have to change everybody in the system. And so, cancer is a complex system, and cancer interacts with the somatic cells around it, as well as with the immune system. And the immune system interacts with everything else. So, I think cancer is not just a molecular Darwinian selection, but it's a defect in the system, and we'll need a systemic solution.
Well, that's good. I didn't think so either. So that's good. Glad that you're not caught up in that. Yeah. Well, very good. What would be a super happy result for you to achieve or figure out in the next few years?
super happy will be, can we find predictors of cancer that will allow us to detect cancer extremely early and prevent the death and morbidity that is caused by cancer? Could we use, systemic epigenetic approaches that can prevent or intervene in cancer without you having to resort to, the poisons that we're treating cancer patients today?
Yep, definitely.
And it's similar for the mental health system. We have an epigenetic approach that will reverse drug addiction or PTSD or chronic pain. These are the questions that we're trying to deal with.
Okay. Well, excellent. Well, Moshe, what's the best way for people to find out more, to read papers that you put out, to get in touch?
So, we have websites. There is a company that I built just to deal with these questions called HKG Epitherapeutics. And so www.hkgepitherapeutics.com has a lot of information. And of course, any search in PubMed with my name will come up with all the papers.
Yeah, you have an unusual name, so it should be pretty easy to find you. So that's great.
Very, very unusual. So probably you'll find only my papers.
Yeah. Excellent. Well, Moshe, thank you for coming on the podcast. I appreciate it.
Thank you. Bye-bye.
You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and share it with friends. Thank you.